All right, hello. Let's take a look at exercise 8.1, which is the first problem on your chapter 8 homework set. So a mixture contains N-peptane, N-hexane, and N-heptane at equal mole fractions. So Z1 equals Z2 equals Z3, where the term in parentheses corresponds to the component index we will use. The temperature is 55 degrees C. The pressure is adjusted so that 75% of the mixture is vapor, so V over F is 0.75. Well, the temperature remains constant at 55 degrees C. Determine the pressure and composition of the two phases. 55 degrees C, the vapor pressure of N-peptane and hexane and heptane are this. So here's our schematic. So to solve, we will use the illustration of the flash drum above to set up our system of equations to solve. A few notes: F, L, and V correspond to the inlet flow rate and outlet liquid and vapor flow rates respectively. We will solve using the fraction vaporized, V over F, and the fraction remaining liquid, L over F. So we won't define an extent of our system, but we'll compute everything relative to the feed rate. The inlet liquid and vapor phase mole fractions of component I are given by Zi, Xi, and Yi respectively. Finally, note that specifying the temperature is equivalent to specifying Pi sat. With that, we are ready to set up our system of equations. We will end up with a total of 8 equations with 8 unknowns. So for our 3-component system, we can write 3 isofugacity or equilibrium expressions, 3 mass balances or equivalently mole balances since we have no reactions, and 2 constraints that are liquid and vapor mole fractions sum to 1. Cool. Since we have a system of linear alkanes, we can assume Rayleigh law is appropriate for our isofugacity expression, and this leads to the following system of equations. So here's my isofugacity equations. Here's my 3-component mole balance expressions. And then there's my 2 constraints. And then to get our final expression, we divide through by F. All right, and we have such. Okay. This results in a system of 8 equations with 8 unknowns, which we can solve. Our 8 unknowns are my vapor composition, my liquid composition, fraction remaining liquid, and my pressure. When we solve, note that all of the unknowns except P will be between 0 and 1. We can use the values of Pi sat in bar, and so if we do that, our final pressure will be in bar. Then here's what I obtain when I solve. Okay, cool. And I'll set this up as is in MATLAB and solve using fsolve. My only note is I have 3-component mole balances. Since we know that we were given that is it fraction vaporized or fraction remaining liquid, V over F is 0.75. That means L over F is 0.25. And so we can actually eliminate one of our mole balances and just essentially have a total mole balance. But we'll keep this as is for now, right? It should be the same. It's just one equation we could in theory solve outright if we wanted to. All right, so let me jump over to MATLAB. And so if I'm trying to solve this with fsolve, so I have a system of equations, and so I'm going to solve it with MATLAB. And so I'm going to start by creating a new script, and then I'm just going to jump right in, and I know I need to create an error function. Okay, so it's going to be function res is equal to, I'll call this air flash, all right, since it's a flash drum, and it's going to have an input, and I'm just going to use capital X. So remember, if I'm trying to solve a system of equations using fsolve, the first step is I need to write an error function. My error function can have a single input and just a single output. What I do, or the strategy I follow, is for this input variable x. So in our case, we had 8 equations with 8 unknowns. And so those 8 unknowns are going to be packed up into this single variable x. So within my equations, I could reference the first through 8th element, and I just need to be able to keep track of it. And what's important, though, in terms of keeping track of it, is the order of the variables here in this vector x is going to be the same as the order of my initial guesses that I provide when I attempt to solve. It's also going to be the same order as my solution when I solve it using fsolve. And so what I have a tendency to do is I call it unpacking. Okay, and what I'm going to do is I'm going to take each element of x and I'm going to assign it to a variable which is going to look like the variable as it appears in my final equation. right? And what I mean by final equation, my equations as I have them written out here in my system of equations. And so the unknowns I'm trying to solve for, right? So I have my y's, my x's, my fraction of remaining liquid, and my pressure. Okay. So when I unpack, if I just keep it in that order, okay, I'm going to say y1, right, is going to be the first element of big X. Y2 is going to be the second element. Y3 is going to be the third element. Okay. X1 is going to be the fourth element. X2 is going to be the fifth element. X3 is going to be the sixth element. LF, the fraction remaining liquid, will be the seventh. And then pressure will be the eighth. Okay, great. So now that I have it packed, so now my question is, do I need to pre-compute anything? No, but I'm going to take the values of my parameters and I'm going to assign them to variables. And so what I mean by that is we're given P1 sat, P2 sat, and P3 sat. So I'm going to assign the three of those to variables. And we're also told that Z1 equals Z2 equals Z3 is equal to 1/3. And my fraction remaining, or my fraction vaporized is 0.75. Fraction vaporized is 0.75. So I'm going to come over, okay, and I'm going to say VF is equal to 0.75. All right, and I'm going to note that when I do that, it is tempting to write LF is equal to 0.25, and I could do that, okay, but then that would correspond to, I just solved my overall mass balance, or my total mass balance, outright. And so then I would reduce my system of equations from being 8 equations with 8 unknowns to 7 equations with 7 unknowns. And so I'm going to set it up as is, we'll solve it, and then we could always go back and we can check this out as well, okay, and what that would look like. So I have my fraction vaporized, okay. So let me make a note. So this is my fraction vaporized. Okay. My vapor pressures in bar, right? And as long as my vapor pressures is in bar, my pressure I'm solving for will have the same units, bar. So P1 sat's 1.903. So 1, not 11. Okay, P2 sat is going to be equal to 0.644. P3 sat is 0.231. Okay, great. And then in terms of my z's, right, I could have 3 z's, or I'm just going to have one variable z. Say z1 equals z2 equals z3. Let's just say is equal to z, and that's going to be equal to 1/3. So let's just say z is equal to 1 divided by 3. Okay, great. So now that I have my parameters, the next thing I'm going to do is I'm going to write out my system of error functions. I'm going to write out my system of error functions. Okay, and so the key of this is, let me make this bigger. So when I write out my error functions, is I go to my system of equations, okay, and I need to rearrange my equations so they evaluate to 0 when I find my solution. And so what I'll do for all of mine is I'll just take the right hand side of my equalities and bring them all over to the left hand side so that I have an expression that equates to 0. Okay. So what will that look like? Right. So in terms of my equilibrium expressions, okay, I'm going to say res1, right, the first element of my vector that's going to get returned, right, I just have one output. Res1 is going to be y1 times p1 sat minus, okay, sorry, y1 times p, okay, then minus right hand side x1 times p1 sat. Okay, My second equilibrium expression is going to be y2 times p minus x2 times p2 sat. My third is going to be y3 times p minus x3 times p3 sat. Okay, so there's my three equilibrium expressions. Okay, next I have my mole balances. Okay, as such, and I call this V over F. So I'm going to bring my right hand side over to the left. So this one will be res, so 4 is going to be equal to Z1 minus Y1 times, then I just called V over F VF, then minus X1 times LF. Okay. And actually I'm not going to call this Z1, right, because I just used the variable Z. Okay. I'm going to copy this. So then res 5 is Z minus Y2 times V over F minus X2 times L over F. And 6 is Z minus Y2 minus X2 Y3 minus X3. Then my seventh, now I'm on to my constraint equations. This will be 1 minus X1 minus X2 minus X3. And the eighth is 1 minus Y1 minus Y2 minus Y3. Okay, so there's my error function. Okay, and so I could set up a script to call this and solve, or I could do it by creating a function with no inputs. Right? It's all the same. Okay, so I'm just going to create a new top function with no inputs, and it's going to be, I'm going to call it my flash solver. Okay, it's going to have no inputs. This would be the same as creating a script just to call this. Okay, and what I'm going to do is let me first come up with my initial guesses. Okay, so in terms of initial guesses, I'll call it, say, IG. Okay, so what am I going to do? I need 8 initial guesses. Right, we know that our first 7 are going to be between 0 and 1. Okay, so what could I do? So I could do, so let me call it, say, IG1. I can do rand 1 comma 7. Okay, so those are going to be random numbers between 0 and 1. Okay, and then my total IG, right? And actually I could have, let me just pack it all in one. So my first 7, right, are going to be random numbers between 1 and 7. Okay, then I'll add on my 8th. My 8th will be my pressure. My pressure is going to be somewhere between all my P1, P2, and P3 sats. And so let me just guess, say somewhere between 0.6. Okay, cool. And then I'm going to say when I solve, so solving, okay, res is going to be equal to then fsolve at error flash subject to my initial guess. Okay, and I could have just as well put my initial guess directly in there, but so be it. Okay, so now I have this function with no inputs, so I could just run it, say sol is equal to flash solver. Okay, and running, oh, I didn't suppress my output in here. Okay, but running, I get this, right? I get this. I see that L over F is 0.25, which is exactly what we said it would be. So in terms of Y's, 0.4055, 3463, 2482, 1167, 2946, 5887, 0.25, and 0.5479. All right, so we solved it. Yeah, and that's all there is to it. All right, and then I created this top function. You could have created a script, but that way, then if this were an exam, all I would need to do is run it and confirm I get the correct answer. So that's a valid solution. Okay, just comment is I said in here, right? We're told V over F is 0.75, right? So then I know, oh, the fraction remaining liquid must be 0.25. Okay. What's key though is if I do this, right? Well, then that corresponds to I'm actually solving my overall mole balance. And so if I were just to specify that L over F is 0.25, what would have to happen up here is, well, I'm no longer solving for L over F. P would become my seventh input variable, and I would have to eliminate one of my equations. Okay, one of my mole balances, right? Mass balance, mole balance. And then I just update this. Okay, and so if I do that, then this, right, 1 through 6 now would just be between 0 and 1. And if I solve, right, I get the same result. Yeah, I get the same result. Only now L over F isn't displayed, but I could print it, right? It's just I solved, my mass balance, right, explicitly outright. Okay, and so I'm just going to switch my code back for when I upload this, just so you have the original solution. Okay, but just note that if you were to go ahead and specify that L over F is 0.25, right, that's okay. Just remember though, you just solved then your overall mass balance, and so you would need to eliminate one of your mole balance design equations. There's equation 1, or problem 1. Let me know if you have any questions.